from 2015 to 25, combination of MPCs with AI algorithms like reinforcement learning algorithms were introduced, as well as data-driven MPC were introduced for robotics to make it as an intelligent robot. For example, apart from the robotics, actually the self-driving cars and multi-robot collaborations for different applications like swarm robotic applications, so vision-guided manipulation. For those different areas, MPC and hybrid versions of MPCs were used. Then from 2025 beyond, again, we are expecting to have cognitive MPC, different version of MPC for making the robots more intelligent, more emotional, and more intellectual. So that is what we are expecting in future in this evolution of MPC algorithms coupled with the learning. Then the next topic is on the reinforcement learning. As you all know, the machine learning algorithms mainly can be divided into three: supervised, unsupervised, and apart from that, we can see another section, reinforcement learning. So that is what we are using in robotics, reinforcement learning algorithms, right? So here actually, this algorithm is more towards the AI and very familiar with the decision-making process of human beings. So as you can see here, in the first two, supervised and unsupervised, we all are working with data and classification, clustering, or regression. But here we have a different type of approach in learning part as well as entirely the algorithm. So the action is taken based on the state and feedback is given to the model agent. Model agent is the robot, for example, and rewarding and the rewarding system is there. Right? Rewards are given based on the action taken or executed. So then, likewise, the algorithm will be trained bit different from the other two learning techniques. Okay, so this quick overview of the reinforcement learning algorithm graphically, that the input data and the input raw data will be given, but here the main thing is that environment is involved, and it's a repetitive process between the environment and the agent. So the agent should be learned interactively, connecting with the environment, considering the rewards or penalties based on the action needed to be executed. For example, if you consider this right side figure, it's a maze solving. The robot has to go to the goal, but if the robot has selected a wrong path, the punishment will be given, or penalties, for example, -10. If I selected the correct path towards the goal, then rewards will be given. So likewise, that learning part is much similar to what the human beings are trained. Right? So because of that, this reinforcement learning algorithm is more like the learning part of the human beings, and it is much closer to or what is we are expecting from the robot. Okay, then if we consider the reinforcement learning, right? If we consider all the reinforcement learning algorithms, we can divide them into main two categories: model-free and model-based. So most of the cases we are dealing with model-free reinforcement learning algorithms. Otherwise, we have to have a model. Right? So, for example, if we go with model-free reinforcement learning algorithm coupled with the model predictive control, then we can combine them together to have a very good combination for decision making part of the navigation process. So here, if I consider the model-free part, model-free algorithm, so we can see again two main categories: policy optimization algorithms and Q-learning algorithms under model-free reinforcement learning. Okay, from them I have selected three for our studies. The first one is Q-learning algorithm, which is a very famous and very familiar algorithm, those who are dealing with reinforcement learning in robotics. So it has a kind of table which will be updated based on the actions taken. So then the status will be status and the actions will be updated in this table, and the best solution will be selected. The optimal action will be selected. Then if I just go to this flow chart or the block diagram representation, there we can see the dual reward technique. So for example, so we have tested this algorithm in our study last year, actually, at static reward and dynamic reward, the dual rewards. Then the static reward is actually is a constant and does not change during the task. And dynamic rewards are changing based on the robot's actions and changes in the environment it is being used. And then the Q-learning algorithm will update this Q table, and then the best optimal solution will be, or the action will be taken into execution. The second algorithm is experience memory Q-learning. It's a kind of advanced version of the Q-learning algorithm, but here apart from the action and status, we have update, or we have maintained the experience of the robots in the table. So apart from that Q table, we can see EM table is there. Right? So if I just go back to the previous block diagram, here the Q table is there, and here apart from that EM table, along with the Q tables, are there where the experience is transferred into recorded values, and status, action, and the experience all are recorded for better performance of the robot navigation. So we have observed that comparing Q learning algorithm and the experience memory Q learning algorithms, this has shown the better performances compared to the Q learning. And later we try to implement proximal policy optimization. So it's a kind of different approach in reinforcement learning algorithms that helps an agent to learn how to act in an environment. It's a type of policy gradient method known as the policy optimization. But the thing is, its stability and efficiency is considerably high compared to the previously introduced two algorithms. Okay, so here these are the kind of features of this proximal policy optimization, and the policy will be again updated based on the experience as well. And the adaptation, as I have mentioned, the last adaptation efficiency of the PPO algorithm is high in dynamic real-time real-world environments compared to the previously discussed two algorithms. So we implemented this PPO in our robot as well. Then this a rough flow chart how the signals flow in the algorithm, just to give you a quick understanding about the difference between the Q-learning or EMQ learning and the PPO. So just looking at those three functional block diagrams, you can see this is a kind of different algorithm in reinforcement learning. The agent has some sort of policy, and reinforcement learning will be updated here in the middle, updated the policies according to the action and the observations based on the environmental changes or the environment where the robot is being used. Okay, comparing those three algorithms together, we can see the learning speed is fast and stable in PPO, and the generalization is also good, and smoothness and how smoothly the turns are taken by the robot is high in PPO algorithm. Then real-time suitability, it is comparatively good in PPO with these two reinforcement learning algorithms. So finally, we decided to use PPO in our study. So then this is what we have implemented in our robot. Model predictive control for obstacle avoidance and path planning, basically the navigation, starting from initialization, taking the environmental reading through the camera, slider, and other sensors implemented, then detecting the dynamic obstacles and static obstacles in the environment based on the kinematic of the model, applying those information to the optimization algorithm, that is MPC, and we come to how to move forward up until the mission is completed. Then this is MPC, but what we are targeting is the learning MPC with the learning part along with the reinforcement learning. So here we can see the learning part is there, the bottom of this figure. The top part is the model predictive control, and measurements are taken through the sensors to the learning algorithm as well, and given back the decisions to the model predictive controller. So this is a little bit complicated algorithm, but this is how we can combine model predictive control and learning together. And this is the platform we used, Jet Auto, which is a kind of AI robot, little bit costlier one. and it has ROS2, Jetson or in board with depth sensors, LiDAR, then YOLO as well. So we have implemented that in our robot platform along with other traditional and well-known algorithm, for example, SLAM and other obstacle avoidance algorithms are being used. Apart from these learning MPC. So this is a part of our research work. And just to give you kind of curiosity and kind of idea about how we integrate advanced controls and learning together for better robot navigation, for example, intelligent robot navigation. So there are plenty of applications, for example, autonomous car nowadays. This is a big topic, right? They are using model predictive control like advanced control techniques along with the learning algorithms. Right? In factory automation, aerospace companies and kind of yard automation or good handling. So these are a couple of applications where we can use learning plus advanced control techniques together for autonomy. Okay, this is our team, and I should express my sincere gratitude to the PIFA for funding this project. And Professor Lilan, the Professor Nalini is also on board with me, supervising our students. Two of them are from different countries, Australia and Finland, and one is from Sri Lanka. And here there are 6 students. Those are final year students following our electrical and electronic engineering course. Okay, thank you very much. That's about the learning MPC plus intelligent robotics. Thank you very much.
Thank you, Dr. Tarinthi Virako. Next presenter can continue with it.
Dr. Jahan, I think I'm unable to share my presentation. It says host disabled participant screen sharing.
No, you can try that.
So good morning, everybody, to everyone. And first of all, could you please let me know whether you can see my slides?
Yes, we can see that.
Okay, thank you very much. So the title of my presentation today is Machine Learning at the Forefront of Intelligent Wireless Communications. And in detail, specifically, I will discuss about some physical layer design examples related to machine learning. So my name is Dr. Himal Suravira, and I'm from Department of Electrical and Electronic Engineering, and my specialty is on wireless communication. So previously, I think Dr. Tarindu mentioned about the applications of machine learning in the areas of robotics. So the aim of this talk is to present applications of wireless communications which uses machine learning for design. So the main goal of my presentation is to give you a brief introduction to these specific areas rather than going or dwelling into deeper into these topics. So what I will do is I will try to inspire you, or I'll try to make your interest in these topics. So in future, if you have any questions, I'm free to answer them as well. So in addition, as Dr. Tarindu mentioned, most of this research that I will discuss with you today are due to our students as well as my research collaborators international research collaborators. Although I have not named them in these slides, I would first of all, I would like to thank them for their sincere contributions and collaborations with me. So since the topic is about wireless communications and how machine learning is helpful to design wireless systems, first of all, I would like to discuss a little bit on wireless evolution. So there are different types of wireless systems. For example, I think you all have heard about cellular systems, Wi-Fi systems, sensor systems, as well as satellite-based communication systems, and so on. So among these systems, cellular systems are popular. And if you know about the evolution, they have evolved from 1G to 2G to 3G to 4G to 5G wireless systems at the moment. So now people are also talking about 6G wireless systems. In particular, 6G wireless systems will be benefit from the use of machine learning design. So these 1G systems were very kind of unsophisticated compared to present day 5G systems. They were based on just analog voice, and then it was improved to digital voice in 2G GSM systems, and 3G era came with the packet type of packet switch data and voice services. WCDMA was the technology used for 3G systems, and then came 4G systems around 2010, which used LTE Advanced and OFDMA, that type of technologies, and they were based on all IP networks and so on. So, and then with 5G, although still in Sri Lanka, we don't see much of 5G networks. It was based on technologies such as massive MIMO, and then also the performance of these systems are fairly advanced compared to earlier 4G, 3G systems with low latencies and speeds up to 10 gigabits per second and so on. So another pattern with this that you will observe with this slide is that every 10 years, roughly every 10 years, we are witnessing the deployment of a new generation of wireless cellular system. So with that, everybody can predict easily that around 2030, there will be a new generation of wireless systems, which we call as 6G. So here are some of the basic requirements of 6G systems. So we talk of everything in extreme high levels. So for example, 6G networks are, have goals to deliver extreme high data rates, extreme coverage, extreme low energy and cost, extreme low latencies, the delays involved in the communication network, and as well as reliability should be very high. And also it should connect, this kind of network should connect a large amount of nodes, or we should expect extreme massive connectivity. So these are some of the key features of 6G. And like say, as I will describe you, machine learning is a good tool, or like say it enables to achieve, it will help us to achieve these kind of 6G requirements in future. So currently 6G research is happening, and around, for example, 2027-28 period, it might get standardized. So, and then around 2030, these kind of systems will be deployed worldwide. So there are particular technical challenges that involves with wireless systems, and these challenges I will explain in short and very fast, so that some of these challenges will motivate you to use machine learning type of designs to solve these challenges. So first of all, I think all of us know the main challenge of wireless communication system is something called multipath propagation. So when you have a transmitter and a receiver, the signals transmitted from a transmitter arrives at the receiver with random phases as well as random amplitudes and so on. That is called multipath propagation. And since these phases as well as amplitudes are random, they will add most of the time destructively rather than constructively. So when these signals are destructively, the received signal power is very low, and as a result, the bit error rate will be high, as well as other performance metrics will be low. So this is a technical challenge. So how to overcome the effects of multipath propagation? So the second challenge is the limited spectrum limitation. So that means, I think all of you know, most of the wireless systems utilize radio frequency part of the electromagnetic spectrum. And since the wireless communications are very popular these days, most of these spectrum has been allocated for various kinds of applications. And as a result, basically, if you have new applications like 6G, it's kind of difficult to allocate new spectrum. So, but since we cannot just sit and wait by just saying that we don't have enough spectrum, so we have to find innovative, spectrally efficient techniques or technologies to overcome this challenge. For example, we have something called frequency reuse in regulated spectrum, and as well as, so in regulated spectrum, the person or the operator who has this spectrum has the sole right to use this spectrum. So in order to improve, let's say, communication services to deliver to many users or devices, then basically we need to provide them with different frequencies, and then these frequencies can interfere with each other. So that is why this becomes a challenge or some kind of a problem that we need to solve. Similarly, in unregulated spectrum also, these kind of interference scenarios can come up, and then we need to come up with innovative solutions to overcome this, to control the interference and to provide better services to the users. So a third challenge could be the limited energy challenge. So as you know, since wireless communications have become very popular, there are a lot of base stations every day getting deployed in different kinds of locations all around the world. So these kind of base stations lead to improved energy usage, and as a result, it can increase greenhouse gas emissions as well as pollutions and so on. So there's a lot of interest to reduce the energy consumption of ICT or energy consumption in wireless communication. So there are a lot of techniques already proposed to overcome this problem. However, like say current set of technologies or approaches tend to show certain limitations, and by applying machine learning kind of tools to solve this problem, maybe in future better solutions can be obtained. So finally, another technical challenge in wireless communication is the user mobility. I think all of you know that earlier systems tried to cater for static users or users that don't move or move very slowly. But nowadays, like say, due to heterogeneous applications, people wish to have communication even when they are traveling inside a very high-speed train. So as a result, this becomes a very challenging thing, because when the user moves from one location to another location pretty fast, the control of the user should be handed over from one base station to another base station. And if the network doesn't allow very low latencies, most of the time during the traveling period, the call will get dropped, or communication quality of service of communications will reduce drastically. So I will not go into much of details about machine learning. With machine learning, I think it's a branch of AI, as we all know. So it allows computers, or it deploys certain algorithms to self-learn from training data and to improve over time without explicitly being programmed. So as you know, machine learning has been deployed for various kinds of applications. For example, for classification applications, whether to understand what is in an image and so on, as well as to predict data, future data, as well as to find patterns within data and so on. So AI, on the other hand, is a broader concept which involves machine learning as well, and it allows us to learn agents, or let's say robots or any device, to learn new skills as well as to solve problems much more in an autonomous way, similar to humans. So this is machine learning. And deep learning, I think also these days is very popular. It's a sub-branch again of machine learning. It's a specific set of algorithms that can be used to deploy machine learning algorithms. So there are different types of neural networks or machine learning architectures. I think all of you might be very familiar with them. The basic one is the artificial neural network, and then we have deep neural networks, recurrent neural networks, as well as convolution neural networks, and finally things like recursive neural networks, long-term, short-term memory, long short-term memory, as well as gated recurrent units. So these kind of different neural network architectures are helpful in different domains. For example, deep neural networks as well as convolution neural networks have been successful in the areas of image processing, whereas with RNN, LSTM, and GR, they have been used to in time series or for signal analysis and so on. So these kind of architectures, what I will show to you today is that they will also be very much helpful to deliver, to integrate with certain wireless communication systems to achieve a better performance, as well as to, in other cases, to optimize certain resources as well. So why we want to apply machine learning in wireless systems? So there are many reasons. So I will just elaborate some of the main reasons. So as the slide says, wireless systems are getting very complicated. So they are affected by human, as I described to you, mobility. Mobility patterns are heterogeneous as well as diverse, and then the amount of data required by users also drastically vary. So there's a variability in traffic, as well as different types of noise, as well as interference patterns are also highly dynamic. So of course, it doesn't imply that the current systems have failed. Current systems function based on, for example, classical Maxwell equations, information and communication theory, modulation techniques, as well as robust coding schemes, etc. But these kind of techniques tend to show certain limitations because of these complexities involved in the emerging wireless systems. So it says, as I mentioned in the third dot point, it says, however, traditional design approaches, which are based on rule-based as well as optimization-based, they show limited adaptability. On the other hand, machine learning offers intelligent data-driven solutions to handle these kind of dynamic wireless environments. So that is why the application of machine learning for wireless system design has come to the forefront. So there are two aspects. One aspect is machine learning can be used to, for example, design and optimize wireless systems. And on the other hand, in certain other applications, wireless systems can be used to enable machine learning applications. So at the beginning of this presentation, I will quickly go through some of these systems that we have researched on, as well as other people are talking about on machine learning, how machine learning can be used for wireless systems. And at the later part of the presentation, I will discuss how wireless systems can enable machine learning applications as well. I'll give you two examples. So now the next slide says how machine learning improves wireless system design. So machine learning enables adaptive resource allocation. So in communication systems, the most important two resources are the spectrum and the power. So these spectrum, how much of frequency, what are the frequency bands that should be allocated to support certain services, users, etc., is a complicated problem. So machine learning can be is a useful tool to solve this kind of problems, along with power allocation. Then, all communications are interrupted by noise as well as interference coming from other networks. So how to manage interference as well as how to cancel noise and to recover your useful signal. Again, of course, you can deploy classical algorithms, but machine learning also is helpful. So that is another way of how machine learning improves wireless performance. Then for network planning, what are the optimal places these base stations should be placed, as well as I mentioned, how to tune parameters involved inside base stations like power, as well as, for example, the time allocations, frequency allocations, all those kind of parameter tuning can be performed. And finally, signal processing enhancements means the channel estimation. Like say in wireless communications, the channel is wireless or just AR. So, typically the channel will introduce you a phase shift as well as an amplitude attenuation on the launched transmitted signal. So these things can be, in order to estimate these kind of things, machine learning is helpful, as well as to recognize what type of modulation schemes are being used at the transmitter, and also to correct errors within bits. Also, these kind of techniques can be deployed. So I will quickly go through due to the limited time. So basically, one application I'm going to talk today is about visible light communications. So as you know, like light can also be used in addition to wireless. Light is also part of the electromagnetic spectrum. So light can be also used in addition for illumination purposes. That is the main use of light. To also deliver, let's say, bit transmissions. So you might be wondering how it can be done. So basically, for example, you can use a LED, and then without detecting to the human eye, you can switch it on and off at a very high speed, so that it will represent a particular bit stream of information. So basically, the left-hand diagram shows you the location of visible light along with a broader spectrum of electromagnetic radiation. So you can see that, say, you have gamma rays, X-rays at the high extreme end, then you have UV, and then you have the visible light spectrum. And below the visible light spectrum is the infrared, microwave, and so on, the radio part of the radio frequency spectrum. So anyway, so this right-hand diagram shows you transmitter, a simple version of a visible light communication transmitter and a receiver. So the transmitter, the main element of transmission is the LED. So you have the data source. The data source is modulated, and then you use some kind of LED driver to drive a LED, and then the LED will switch on and off at a very high rate. So at the receiver side, the main device is the photodiode, which converts the received intensity into a current. And then this current is since it is small, you can amplify it and convert it into a usable voltage using a transimpedance amplifier. And then you can do the inverse operations of such as demodulation, and also to detect the data. So basically, this is the visible light channel model that most of research papers use. It is called the Lambertian emitter model. It involves certain parameters like angles, incident angles, half power angle, and so on. I will not go into details. And also the right-hand side diagram shows you the beam that will be emitted for different half power angles. So you can see, when the half power angle is small, you can see that the beam becomes very narrow and sharper, so that the signal to the receive signal to noise ratio at a particular location can be increased. However, if you want to provide services to a broader, to improve the coverage of the area, you need a much wider beam. So that can be achieved by increasing the half power angle. But the downside of it, or the disadvantage of this, is that now you will create interference to many users by spreading the transmitted beam or the light beam. So there are different trade-offs that you can discuss about narrow beams, wider beams, and so on. So clearly, you can see how machine learning will enable intelligent decisions to be made depending on the context of the users. For example, if the users are clustered, maybe it's better to use narrow beams. When the users are spread apart inside the room, typically visible light communication is used in an indoor setting. So maybe wider beams are preferable, and so on. So this is the received signal power when, let's say, the transmitter or the LED is located at the middle of a room, and then this is just a simulated transmitted power. just for you to get an idea. So in the middle, you have a large power, receive power. And as you go to the north, south, or the east, west directions within your room, the receive power drastically reduces. So there are a lot of applications of VLC. I will not go into detail. So just like Wi-Fi systems, there's some system called Li-Fi, which is based on visible light, as well as you can apply it for vehicular communications, underwater communications, and these days for Internet of Things, and also along with UAV communication or drone communication. Okay, so there are a lot of applications and there's a lot of interest. And I will show you one example of how machine learning can be used for this kind of a visible light communication system. So the mini title of this slide, this work is called Channel Estimation and Prediction for Spatial Modulation Visible Light Systems. So first of all, I will introduce you what do you mean by spatial modulation. So spatial modulation is basically, now let's say you have 4 LEDs, and then for example, depending on the activation of a particular LED or 2 LEDs or 3 LEDs, that will create some kind of a spatial signature at the photodiode or at the receiver. So in other words, for example, if one LED is lit up, it will create a signature, and if another LED is lit up, it will create a different spatial signature at the photodiode. So these kind of differences can be used to convey bits in spatial domain. Say for example, now since here there are 4 LEDs, if the photodiode can detect that LED 1 is on, you can use it to convey 0 bit. And then if 1 2 is switched on and others are switched off, you can use it to convey maybe 1 0 and so on. So this combination that is shown in this figure is helpful to convey additional 2 bits in spatial direction, in addition to whatever the modulation that you have used. So this is spatial modulation is some kind of a spectrally efficient communication system. So the detection for this system happens, in this, before that I will quickly describe what is the environment or what is the situation that we consider. Basically, in this environment, what we have considered is the user is moving within the room, and the orientation of the receiver is also it's not purely random, but it varies because, for example, let's say a laptop is taken inside the room, the orientation of the laptop can change. So basically, since the orientation of the receiver changes, the detection happens in this way. The received signal and the channel, and this is the transmitted signal SN. So by estimating the transmitted channel, the channel H, you can calculate according to this metric, which is called the maximum likelihood decoding. You can be used to estimate the transmitted signal. Okay, so basically with that, it is very clear that we need to first estimate what is the spatial signature, or in this case the channel. So for that, like say you can apply what you call, in a complex environment like this, which I explained to you, due to movement as well as random receiver orientations, a machine learning approach. So I will skip these slides a little bit because it talks about how we model the user mobility, and also like say how we model the random receiver orientations and so on. So I'm pretty sure you got a basic idea of the problem that we have solved. So I will skip these slides and I will quickly introduce you the channel estimation frame structure. So basically what we are going to do now is that we will consider a particular time frame of window. And then at the beginning of, so these windows will be subdivided into blocks. So at locations which we call as pilot locations, which we will estimate the channel or H value. So then we have then what we will do is, now if you want to estimate the channel at every block or every time interval, it will introduce a lot of burden on the system computation. So what we do is we will measure only at pilot locations, and what we will do is, like say, we will try to predict the channels in the middle. So that is, the green ones are the predicted channel, as the orange ones are the pilots channels. So basically, that is the main idea of this solution. So for that, of course, you can use classical approaches like linear interpolation, spline interpolation, and as well as something called piecewise cubic Hermite polynomial interpolation, and so on. But in addition to that, since these the orientations as well as movement of the user is also modeled into our system, it is kind of becomes a complicated system. So what we thought was just to use a very simple artificial neural network architecture. So here, like say, it involves an input layer as well as two hidden layers with nodes. I think there are NR nodes at each of these two hidden layers, and then you have this output layer which will predict, right, or which will predict the channel location, the channel values at these intermediate block points or time scales. So the white values will be predicted using this artificial neural network. So that is why I mentioned this as an application of machine learning for wireless systems. So I will not go into details because there are so many details. The idea, as I told you, is just to give you a basic idea and kind of interest on different options that you have to apply machine learning. So basically, anyway, what we have shown out of this result is that in this, when you have, of course, perfect channel knowledge, that is the best that you can do. So this one was considered as a baseline scheme just to see, like say, how effective is our ANN-based solution now. So basically, you can see that our ANN-based solutions under various user velocities as well as under different orientations are capable of predicting the is capable of lowering the bit error rate, because lower the bit error rate, better the system performance is. So anyway, this is one application of machine learning in wireless systems. So there are certain, in addition, there are certain challenges of visible light, like how to increase the robustness against noise, because as you know, since it is light, sunlight, lights from other lamps, power sources, all those kind of things introduce additional noise into the received signal. So how to, for example, how to model them as well as how to predict them and remove them, you can use machine learning, as well as to increase the communication range, as I discussed earlier. Narrow beams are not good for increasing coverage. Wider beams are good for increasing coverage, but there is kind of a trade-off between interference and coverage. So all those kind of things can be solved by applying particular kinds of machine learning algorithms. Okay, so that is why I mentioned these as challenges. The next application I'll quickly go and discuss due to limited time is deep reinforcement learning for risk-assisted full duplex transmission. And basically in this, this is another example where reinforcement learning, I think Dr. Tarun discussed about how reinforcement learning applies to robotics. And here, like say, this is a work that we did last year with some collaborators from India to apply reinforcement learning for a wireless system design. Okay, so what is a RIS? So RIS is just like IRS stands for intelligent reflective surface. So basically, it's just a planar surface with a lot of elements. And so what happens with this kind of an element is that when the received signal falls into these elements and the reflected signal out of these elements can be controlled with different phase values, as well as in certain cases different amplitudes. That means power can be changed, as well as in certain other cases polarization as well. So by changing, now if you know, reflection is orderly kind of behavior. Okay, so the incident angle is equal to reflected angle, but by software controlling as well as applying currents through devices like pin diodes. So basically, the reflected signals, angles, as well as amplitudes and polarization can be changed. When you do that, so basically what happens is that at a particular location of a receiver, the signal strength can be improved because it is like pointing a beam towards a particular X, Y, Z coordinate in your environment. Okay, so with that is what is called as a IRS. So already there are a lot of prototypes being developed across different countries, as well as certain companies even deliver these kind of products. So basically you can use them to improve the receive signal strength at particular locations within your wireless environment. Okay, so basically, sorry, I have moved on to the previous set of slides. So basically, that is what is called a IRS or a RISC. RISC stands for Reflective Intelligence, Reconfigurable Intelligence Surfaces, and IRS stands for Intelligent Reflective Surfaces. Both are, I mean, technically the same concept. So basically, I mean, this is a very popular kind of a system that is being researched on these days. So there are, as I told you, there are a lot of applications of RISC, IRS or RISC. For example, to remove blockage effects, because you can place RISC on a building so that the transmitted signal can be reflected into different directions to avoid blockages by other buildings or trees or vehicles and so on. And also, since it can be manipulated into different regions, you can control the interference, as well as it can be used as a passive relay. That means to amplify, as an active relay to amplify the received signal before it is being retransmitted and so on. So there are a lot of applications, and particularly targeting for 6G. So this system model I will quickly explain to you just to give you a basic idea. So here we consider a base station, and then we consider two receivers, RIS1 and RIS2, and there are two users. One is a uplink user, one is a downlink user. So the downlink user gets services from the base station through the RIS2, and the uplink user transmits to the base station using RIS1 as a aid. So basically, and then the base station is operated on a mode called full duplex. So with full duplex, what happens is you transmit and receive at the same time as well as at the same frequency. For example, current systems are called half duplex, and they are what you call transmit and receive into different time slots or into different frequencies. So when you do this, you can obviously improve the spectral efficiency. But when you improve the one problem with full duplex transmission is something called self-interference. So with self-interference, because since you are transmitting and receiving at the same time, basically what you call the receive side overhears the transmitted signal, and since the receiver is co-located almost with the transmitter at the base station, so this interference can be very significant, and that will limit the reception, or the received signal will not be able to be decoded. So first of all, the main idea of full duplex transmission, if you want to allow it, is to reduce or control this self-interference. In certain papers, it is also mentioned as loopback loopback interference. So anyway, so here what we did was first, sorry, again, I went to wrong slides, set of slides. So basically with this one, basically what we did was we formulated a particular problem, and we used reinforcement learning, because of course we didn't use a kind of a traditional what you call optimization method, because the system was very complex. So we applied a reinforcement learning approach to solve this problem. So what was our objective was to maximize the overall sum rate. So that means now you have two users, uplink user rate. I mean, you know, I think according to Shannon's formula, capacity you can calculate as bandwidth times log to 1 plus signal to noise ratio. So if you consider that as the one of the achievable rate, so then you have the uplink user rate and the downlink user rate. So we consider their sum or the addition, and then we try to maximize this sum rate by changing certain parameters. What are these parameters? The beamforming vectors at the base station, or the weights that you will apply to these multiple antenna arrays to maximize the received signal to noise ratio, as well as the phase shift at the IRS elements, and the power, right? Transmit power for the uplink and the downlink users. So I will not go into details because now already time is getting up. So, like you can, I will also maybe if you are interested in, this is published work. So I will introduce you that published work and how we solve this problem. I think you got some information about reinforcement learning from Dr. Tarindu's lecture. We used reinforcement learning to solve this optimization problem. And then we showed that the results were good. And for example, in future, these kind of techniques can be applied in the context of future wireless systems. So next thing I will quickly go is something called fluid antennas. So as you know, like say fluid antennas are like say, for example, if you take the traditional antennas, that means antennas that you have now, they are fixed. Okay, you cannot move them or you cannot rotate them and so on. So very recently, around 2022-21 period, like say there was this professor from UK who is called Kai Kit Wong, and then he introduced this concept of fluid antennas, where the antenna ports or like say antennas can be moved, like say across the tube of fluid. So basically, I will not go into technical implementations or technology on how these systems can be implemented, but you can think of them as moving antennas across a particular tube. So let's see how this helps to achieve better services in wireless communications. Okay. So anyway, so fluid antenna system is something like this. So this is called a 1D fluid antenna system. The right hand one is called 2D fluid antenna system. So you can see that, say, according to the 1D diagram, there are n number of ports, and these antennas can be positioned. Let's say you have an antenna, and then depending on the signal strength that you want to give to the user, it can be located at a different, desirable location from the top to the bottom. Okay. So you might be wondering why I need to move the antenna. By moving the antenna, you can, for example, increase the signal strength. So basically, this idea can be even moved on to, for example, a 2D structure. So with the 2D structure, basically you have 2 dimensions of movement. So these antenna ports, so the system can choose a particular antenna port. For example, let's say this location is something like, let's say 5 by 5, and so on, so that it will also help to increase the signal, the user signal towards a particular device. So basically now this diagram shows you the one challenge of fluid antenna system. So you can see that when the antenna is moved across this fluid tube, you can see that this is the received signal, how the received signal varies. So the idea is to place the antenna at a peak, right? So the idea is for us to place this antenna at a peak, so that this peak will deliver best performance to the user. So, but then it becomes quite a complicated problem because the channel varies rapidly, as well as, for example, now let's say this movement will also take some time. So when this movement happens, maybe that position is already dropped down to a lower value. So, there are many what you call opportunities or chances where machine learning can help you. For example, machine learning can be used to predict these variable channel coefficients, and then maybe to move to this antenna to a suitable location to supply a better signal strength and so on. So I will not go into detail, but just to give you an idea where it can be applied. So port selection means something like that. So you select ideal ports where the received signal power, or let's say in this case, I took it from a research paper given below, which maximizes the sum rate at the receiver. So you move the kind of antennas into different ports. So of course you can do this by what you call classical optimization algorithms as well, but this becomes highly complicated. So this is an ideal opportunity for you to apply reinforcement learning and then for the transmitter to learn optimal strategies to maximize the sum rate, or else, in other words, to learn optimal policy. So another what you call area we can discuss quickly is something called semantic communications. So in semantic communications, basically traditional communication involves with transmitting bits and symbols, as you know. So basically the motivation draws, as you know, from something called Shannon's theory, and as well as, I mean, for traditional kind of bit transmission. But on the other hand, there's an emerging field called semantic communication. So semantic means transmitting the meaning of data only, not the bits, entire bits, but just transmitting the semantic meaning of the data, so that the data transmission, what you call the amount of data that you need to transmit will be less, as well as on the other hand, since you are transmitting the meaning, that should be sufficient for you to get the job done at the intended application at the receiver. So basically, I mean, so in order to extract the meaning, we use something called a semantic encoder and a decoder at the receiver. So that those are based on machine learning approaches. So this is a good example where we can use machine learning to improve the, I mean, quality of communication. So I will again, sorry, I will go into details of this system very quickly, given the limited time. So basically with semantic communications, earlier like people talk of 3 levels of communications: bit level communication, semantic level, and effective level. So I think with effective level, what happens is the third next step, which is like effectiveness of the received meaning to achieve a desired response or action. So let's say that you are capturing a traffic scenario, okay, and like say traffic patterns within a city, and then you convey to cars or vehicles within roads. So if you do effective communication, so basic idea is that when these what you call images are seen by the drivers, they should recognize that there is a, let's say, a traffic jam in front of them. So they need to divert their cars into different lanes or different roads and take alternative routes. So if you can do that by just sending the barely sufficient amount of information, then that is called effective level communication. Semantic means just to send the meaning. For example, that when you just send certain let's say you take an image and then you only take the lanes or the road parts of the image, and then you transmit only that part, but not, let's say, the trees or buildings and so on. So then that is just to, that will convey the meaning of that image. So people who are receiving that will understand that now there is some kind of a incident happening in front of them and so on. Bit level means, like say, you don't worry about the application or the meaning or the effectiveness, you just transmit the bits related to the entire image. So that is what is done at the moment. So this is just a basic idea of semantic communication. The first one is basically traditional, as I told you, the bit level communication. The second one is just, for example, what you do is instead of transmitting this image, you transmit a mask of this image, let's say, right? And then so how you create the mask is using a semantic encoder, which is based on machine learning algorithms. And then when the receiver sees only the mask, right? The receiver sees only the mask, so it applies a decoder, let's say a GAN network and so on, to reconstruct the original image that was, I mean, that the transmitter wanted to show to you or to the receiver. Okay, so clearly you have an encoder and a decoder which can be based on machine learning. So that is one application. Okay, so then I mean, if you can just give me, so I will skip this part. So I promise that I will also discuss a little bit on, for example, how wireless communications can be used for machine learning applications. I have two very, very quick kind of projects that we did with students. So here one application is that we can use wireless UAVs or drones to capture, okay, for example, images of disasters, and then these disaster images can be conveyed to a server for further processing. Say, for example, to understand what type of damage has happened on the ground level, whether people have been trapped inside buildings or whether buildings are going to collapse and so on. So you can clearly see so that that decision-making part or the understanding part is done using machine learning, and wireless communications will help you to achieve data transmissions in this process. So I will quickly go to the basic diagram and then skip. Basically, as I told you, UAV is going to take images of this kind of disaster-stricken area, and then basically it applies a particular machine learning algorithm, and then it transmits that information to a server so that the server can take informed decisions about the disaster. So one constraint at the UAV is that UAV don't carry battery, sufficient amount of batteries, it's energy limited and so on. So basically what we thought was that the UAV should be, UAV should apply a very simple kind of a machine learning algorithm not to drain its batteries too much. Okay, so for that we design. So for example, then we considered several downstream tasks. That means what the server has to execute. For example, classification. So when the server sees a particular image, it needs to understand, like say, how many buildings have been collapsed, whether, like say, people are trapped, and what are the critical areas of this image where rescuers should be sent, and so on. So that is called classification. And then to answer, like say, some of questions like how many buildings are here in this, in this kind of images, whether this is a flooded area or a perfectly good area, and all those kind of things are based on visual questioning answering, or VQA. So we design a common machine learning pipeline or architecture to address several downstream tasks. Actually, in this case, 2 downstream tasks. So that is the specialty of our algorithm. And then basically what we did was we achieved this using 2 steps. One was that we considered constructing a semantic mask, okay, out of this raw image. And then this out of this semantic mask, we took only the necessary information, or we created a secondary mask out of the segmented image. And then that image is now here shown as in black and white. So this image is transmitted to the server so that the server is being able to achieve classification or to perform VQA and so on. So that is the speciality. So you can see, since this is a black and white, just a simple mask, you can reduce the amount of data transmission, as well as you can reduce the amount of information transmission. So sorry, latencies, so that this network will perform efficiently. So that is what we did. And like I said, there are a lot of details on how we design this pipeline, which I will skip. Okay, so that is the part where wireless communication is helpful to achieve certain machine learning tasks. Okay, so data sets, loss functions, all those things I will skip. Then finally, like I will quickly discuss here what we do is that we want to model the radio environment, or we want to model what is the receive signal power at a particular location inside the room, or we want to model the receive signals strength means power as well, sorry. So maybe we want to understand at a particular location what is the receive signal phase, amplitude, and so on. So that is what is called as radio environment exploration. So for this one, traditionally people have been using analytical based models. For example, you have a transmitter, then you have a receiver, then from the transmitter, let's say you are launching a sinusoidal signal, and then based on reflection, refraction, and scattering properties, which are modeled using physics, people can calculate the received signal, what are the received signals at a particular XYZ coordinate inside the room, and then based on that you can make calculations like the signal strength and so on. So here we use some kind of so that is a kind of cumbersome, means like it is difficult as well as it is time consuming. So what we did was we thought of taking images. Okay, let's say we take images within a room environment, and then this using these images, what we do is we classify, like say what are the objects within that environment, like tables, chairs, people, walls, windows, all those kind of things. Okay, so that is what we do with the images. Then what we do is we applies an algorithm which is based on ray launching or ray tracing in certain contexts. So with ray launching, what happens is we launch multiple amount of rays or signals, and then we allow them to bounce off the what you call off these obstacles, and then using reflection, diffraction, as well as scattering principles. Okay, so then we can calculate the amount of rays that will penetrate through, let's say, a particular user's receive antenna. Penetrate means, like say, the receive antenna has a field of reception. So we will capture all the signals that goes through that field of reception, and then based on that we can calculate the receive signal power. Okay, so basically so this is the methodology we use. So we use object detection based on YOLO, and then we use object localization. So once we identify these objects using machine learning, so we can calculate their locations as well as their properties, like whether they have sharp edges, whether it's a smooth surface or a rough surface, and all those kind of things. And then those inputs are fed to our ray launching algorithm, along with our ray launching algorithm, to calculate the, let's say, the receive signal power. So this is the detail about object detection as well as, for example, localization. I will skip these details because already I have used too much of time. And then we do depth estimation to calculate where these, obstacles are, these objects are located. And then, as I told you, we analyze their properties, okay, roughness, smoothness, all those properties. And then based on those inputs, we will apply them to this kind of a model based on ray. This is our ray propagation model or ray launching model. So as I told you, from this transmitter location, we launch many rays, and then we allow them to bounce off the walls or the obstacles, and then we capture the rays that are being received through the receive signal, the cone of the receive antenna. Okay, signal received. So based on that, we can calculate the signal receive signal power. So that is what we did. So with that, I think, like say, that's my two last slides about what is the role of machine learning for 6G systems, because they are the ones that have been research has been developed. So for the audience, this is a good opportunity to study about these systems, as well as to study various kinds of machine learning algorithms that we discuss. Supervised learning, unsupervised learning, reinforcement learning, and then these days we also have GAN networks, transformers, as well as other things like foundation models, diffusion models, all those kind of things. There are so many applications that you can use them to solve wireless communication. So many tools from machine learning that you can use for wireless system design. Okay, they have been introduced in some of these slides. For example, with supervised learning, you can predict channel conditions, traffic patterns, user demand. With unsupervised learning, you can do user clustering, you can find patterns within users, and then you can do anomaly detection, like, well, let's say one receiver has very low signal power, but whereas other users have very high receive signal power. So then you can isolate that receiver through anomaly detection. And then resource grouping means, like, say, if you want to provide a certain amount of bit rates, you can cluster the users into groups in your cell. So that can be done. And reinforcement learning can be used to can be applied to calculate dynamic spectrum access and so on. And federated learning can be applied to preserve privacy communications, as well as to improve the security. With federated learning, I think you have locally trained models. They have been fed to a centralized server to construct a global machine learning model, and then they are redistributed to the edge servers. so that edge servers don't have, they don't need to know the global data, so that privacy can be enhanced by using that kind of approach. And as I told you, deep learning, generative AI, and finally these days people talk of agentic AI. So all those kind of tools can be applied for the design as well as modeling design as well as optimization of wireless networks. So thank you very much. And if you have questions or any feedback on the tutorial, I'm happy to answer them as well as to receive them. So this is my email address. So with that, I will conclude my presentation. And I hope that you found this presentation informative as well as interesting. So please let me know your feedback as well. Thank you very much.
Thank you, Dr. Himal Suravira. Now another person can proceed that session.
Hello, can you hear me?
Yeah.
Okay. Let me share the screen. I hope you can see my presentation as well. So today, I'm going to talk about a little different approach from the traditional machine learning techniques that you are using. I'll focus more on the agent-based modeling, which is basically used for modeling very complex scenarios. Okay. So how many of you have heard about the agent-based modeling? Can you raise your hand in Zoom if you have heard about it before? Okay, yeah, actually only one person is there. So yeah, I will keep it simple without going into any detail, but I will give you the overview about what is this agent-based modeling and why it is used and what it can do and so on. Okay. The work presented here related to the microgrid is actually a couple of work combined by my undergraduate students as well as one of the MPhil students who is actually now working as a lecturer in the Southeastern University. Her name is Kathleen Sarin Khan, and the other works were done by some of the undergraduate students at the University of Kerala. Okay. Okay, so let's see what is this agent-based modeling. Okay. So how we so I don't know, like whether you're familiar with this image, right? It's taken from one of a very famous movie called Matrix, right? If you have seen the movie, then you might have some understanding about the agent. So this movie actually is focusing on the human entering into the simulated or kind of a computerized environment, right? And there were lots of agents, and these agents behave, take decisions, and they behave autonomously. So this movie kind of gives the whole picture of the agent-based system. Okay. So we will focus on this agent-based modeling, okay, and how we can use to understand the very complex scenarios. Okay. So first of all, why we need to deal with the complex scenarios? Okay? Why complexity matters? Right? Now, if you think about the most of the modeling that you are done at your undergraduate level, so you come up with the equivalent circuits and you come up with the equivalent models and or linear models or nonlinear models, and then you try to simplify them, right? So you focused on one certain entity and try to model it mathematically, right? So that's what we do. Right. But if you really look at what's going on in in your environment or in your world, right? So there's a lot of complexities associated, right? So everything depends on something else. Now, for an example, if I take an example from the power system perspective, right? So we have a gadget called the transformers to transform you to change the voltage from one level to the other, right? But this transformer does not function alone in the power system. It is connected to the other equipment like you have power sources and you have loads and you have regulators and so on, right? So they make a complex model, right? So it's not about the single component that we are talking about, right? So before we going into any this power system stuff, which is kind of more focused on a certain group of people who study the power system, right? We will get a very simple example. So why this the understanding the complexity is important, right? So as I said, you have very independent components in the real world, right? But these independent components have dynamic relation, right? Interaction. Now think about yourself, right? You are an individual component in this world, okay? But now, can you behave as you want in this world? No, right? There are certain rules in the society. There are, your friends are there, and the peer pressure or the peer interest are there. So your behavior in this world depend on the dynamic interactions with the other people in this world, right? So modeling such kind of complexity is not easy, right? To be honest, the modeling the human behavior is the most complex thing that the agent-based modeling try to address. Right? Now, for an example, you will see, like if you dig into this subject, you will see people are trying to model the spread of diseases, how the diseases are spread worldwide. Like, for an example, the COVID disease that we faced very recently, right? So how these diseases are spread worldwide based on the human behavior, right? So that can be done through the agent-based modeling, right? And sometimes people try to model the market behavior of certain products, right? And sometimes even people try to model the behavior of a zombie attack, right? Which has never happened, but they have theorized it, and they try to model how the world will behave and how the human will be suffered or transformed to the zombies during a zombie attack. So those are the very interesting things that people try to model by using these multi-agent systems, which are very complex scenario, right? So we will take a very simple scenario which can be understood by everybody, right? So let's take a hypothetical case, right? Like there is a product called AT, right? Just a name given by me, right? So what this product does is it basically slows down your aging process. So you will be remain younger for a longer period of time, right? So so now imagine now certain company put this product into the market, right? And then how this product will penetrate into the market, right? So the sales dynamic of these products depend on various market factors, like what are the technologies used to build this product, right? Is it the proof of technology? That means whether this technology is proven to be guaranteed that your aging process is slowed down. Are there any side effects, right? What are the ingredients used? Are there causes for cancers or things like that? And then are there any competitors in the market providing the similar product, right? So, and then the consumer behavior, right? So how the consumers will buy, when you think about the consumers, there are certain people who buy anything that comes new to the market just for testing, right? So so there are those kind of people, and there are people that wait for a while and observe the behavior of the product in this market, and the how this affects to the other users, and then they use it. So the consumer behavior is also matters, which is very hard to the model, because the consumer is a human. So human, we argue on certain things, we wait, we observe, we do a lot of things before we try anything else, right? So it's very complex behavior, right? And also external influences like the reactions from the experts, like doctors or the lawyers, right? So they might the depending on the outcomes, there may be one or two cases that went wrong, and the lawyers may take them and try to there are different agendas, right? So how these people will behave, right? So it's very, very complicated situation, right? So this case is very simple. So selling a certain product in the market, but if you really look at the components involved in this process, right? There are a lot of components, and all these things are interrelated, right? So there are interactions between these components, right? So modeling such kind of complex scenario, right? Sometimes the mathematical modeling, we can do mathematical modeling, we can do certain mathematical modeling, and we can do for optimization techniques, right? And very complex optimization techniques. But you will see later on, the agent-based modeling facilitate very very dynamic and very easy to create simulation, right? So, okay. So the typical approach for analyzing these kind of sales is by using the survey method, right? So you can conduct surveys on selected samples, and can provide insight into consumer behavior and so on. But if you have tried surveying before, it's not easy as you think, right? You have to carefully design the questionnaires, right? And then your response rate, I don't know, it's very hard to predict sometimes, you distribute the survey, but you will not get results as you expected. Very limited number of people will respond to that. Then you have to go into them and talk to them, fill your surveys, and it's a lot of process, right? So we can consider the very broader context, right? And when interpreting this the survey results, okay? Right. So when you are doing agent-based modeling or any other modeling, so it's very important to understand the problem, right? So understanding the very complex problem requires in-depth analysis of the individual components in the problem, right? So this is a key to the agent-based modeling. So individual components in the problem will be modeled as agents. Now, for an example, I will quickly go to here and come back. Now, if you take an example from the microgrid, right? So in the microgrid, you have many components. So you have the power grid, right? And then you have solar systems or renewable energy, maybe solar, wind, or something like that. And you have electric vehicles, right? And you can have battery energy storage. So those are the different components in a microgrid, right? So you have to identify these components, okay? And when it comes to agent-based modeling, you can model these individual components as agents. Okay? And I will quickly show you some of the work done by my undergraduate students. So in order to model each of these agents, now for an example, this is a modeling of the photovoltaic agent or the PV agent, right? So electrical students, you are very familiar with they are very familiar with the mathematical model of the PV system if they are doing the power engineering, right? So we can incorporate this mathematical model into our agent to calculate the various parameters, like now what's the input to the photovoltaic system is the irradiance coming from the sun, right? And based on that input, we have to calculate the voltage, current, right? And the power delivered by the photovoltaic cell, right? So that can be done through the set of equations. I'm not going into the details of these equations, right? So, okay, so you can calculate the voltages, power, and so on, and you can derive the VI IV characteristics and the power delivered based on the different irradiance level from these equations, right? So those equations can be embedded into the PV agent, right? But the agents, now your mathematical models stop at that point and do all the calculation based on the model, right? But when it comes to the agent modeling, you go beyond, right? And you incorporate certain other things, which we will discover in later, right? And I will quickly show you the other type of, this is from the solar cell to the PV module and PV array. So you can see it's getting more and more complicated, right? And then the other agents, these are the battery, right? Battery agents, so you can derive the corresponding equation, right? And then you have so you can analyze the behavior of the battery, how the state of charge varies, and so on, and the electric vehicle model, right? Which I will talk about in detail later, right? So you can see like each of these components you will model as a agent, right? And then the agent-based modeling does not stop at that point. So it also models the interactions between the agents, right? So how the requirements of one agent, or the output of one agent depend on the requirement of another agent, right? And then it's also, you need to also understand the imaging patterns and the possible cases to, simulate the different scenarios and to validate your model, right? Right. So any type of modeling, all these things are very important. And when it comes to the agent-based modeling, so identify the individual agents or individual components and their interactions is very important. Okay. So if you look at the complexity of the power system, okay, now it's becoming more and more complex. Now, in the good old days, the power system was not that complex because you had the generations in selected locations, right? And you transmit the power through the transmission line to the what we call the load centers, right? Or the certain towns in the country. So it was always from the generation stations to the load center. So it was not that it was a little complex, but it was not that complex as of today, right? But how things have changed as of now, right? So if you look at the today's power system, I think you are also familiar with. So you can see many, solar generation, right? Rooftop solar are there, and then the solar power plants are there, kind of a large scale solar power plants, and wind generations are there. So in Sri Lanka, we have a large wind generation in the Manor, right? And small hydropower plants are there, right? So everything is now distributed all over the country, right? So it's a distributed generation, right? It's not kind of a coming from a certain non-centralized location, right? The main problem now CB is facing, like one problem for very recent outage is there are the power coming from the distributed solar systems were not visible to the Ceylon electricity board because they were not monitored. So they are coming from all over the places, right? And the consumer behavior, right? So how you use the power, right? It's depend on you, right? So the way I am using the power is totally different from the way you are using the power, right? So when you iron your clothes, when you wash your clothes, right? So all those things, contribute to your use of power, right? So the different consumers behave differently, right? And you have mobile loads and mobile sources, right? The most complicated the thing in the modern power system is electric vehicle because you if imagine that you have an electric vehicle, right? So you park it at your home, right? If you have a solar panels in your home, you may charge it from your home, okay? And if not, you come to your work and you can charge it from your work location. Or you go to shopping, while you are shopping, you are charging it at a shopping mall, right? Or if you are going for a long drive, you do fast charging at certain locations, while you can have a short break, right? If it's a long drive, right? And then, okay, so you don't know where you, not you, but for grid, the where you charge the vehicle will be different for different times, right? There may be patterns, but it's complicated, right? And also with the modern technology, there's something called vehicle to grid, right? So that means so after the whole day drive, you come back home, and if there's a certain charge remaining, right, you can sell it to the grid, right? You can sell it to the grid and some money, right? So that is vehicle to grid. So there may be power, your electric vehicle now acting as a source, okay, to the grid, right? So typically you may dump energy to the grid from your home, but it can also depend, right? So if you go for a vacation or something, you may dump the energy from somewhere else, right? And then the regulatory framework, right? So how much energy you can dump, right? So sometimes the regulators doesn't allow you to dump as much as energy you want. Now, for an example, the solar case, due to this recent power system, there was a request from CEB to reduce the solar power supply to the grid during the weekend, right? So there's some sort of a regulatory measure is taken, right? So there is a control, right? So when all these things comes together, the systems become more and more complex, right? So then how we can model this type of very complex system, okay? Okay. So if you go for a conventional modeling, right? So we can use the conventional modeling approach, which is centralized and which based on the mathematical framework, right? And you use the top-down perspective, right? So if you look at the mathematical modeling of the PV systems, battery energy storage, PV models, so you can see there's a lot of equations involved with it, right? So they may be linear, they may be non-linear. So then you have to handle them, and you may have experience, like when we come across with the non-linear models, we would like to linearize it, around the operating point, right? Which kind of based on certain assumption, which simplified the model, at the same time sacrificing the accuracy of the model, right? So that's how the traditional mathematical model works, right? And the other thing is, as I said earlier, when you are doing the mathematical model, you focused on the individual component. So you build a mathematical model of individual components, right? So we have PV model, battery storage, and EV model, and so on. Okay. But in the complete system, you may have a number of EV models. So very simple example, in this case, you have 4 EV models, right? And then 2 PV systems, 3 battery storage, right? And so on. And then 3 charging stations, CAC stand for charging station, right? So this is a complete model, but in reality, this the model is much larger than this. Okay. So how you go from this mathematical model to this the complete system, right? So you can do the modeling, right? You can form this as an optimization function by using these objective functions. And as the system becomes larger and larger, this objective function becomes more and more complex, right? And there are techniques to solve this. Even the programming language like Python also support many techniques to solve this kind of problem. Okay. Okay, so now let's move on to our topic, which is the agent-based modeling, right? So, okay. So in the agent-based modeling, as I said earlier, so we represent individual components as agents, right? And these agents may behave based on the defined rule or based on certain intelligence we embedded into this, right? So, okay. So any agent like, okay. And then also it's depend on the interact with one another, right? So this agent-based modeling. So you have individual agents and their knowledge base, which can represent using the rules or which can representing as any other knowledge techniques like AI or the reinforcement learning that you heard short while ago, or there are agents called the game theoretic agent, which use the game theoretic approach to model their behavior, right? And then also the interaction with them. So agents does not take decisions by themselves. They do, but it's relying on the others' input and the interaction with the other agents in the system as well, right? So actually, what's the most important thing in this agent-based modeling is this interaction. Okay, so this interaction will lead to emergent behaviors that can capture very complex system dynamics. Okay, and it will provide the insight into underlying process during driving this system. Okay, right. So, okay. So why we need the agent-based modeling for this complex system modeling, right? So this agent-based modeling, as I said, is very capable of capturing the decentralized operation or the distributed operation, right? So in the modern power system, we are also now talking about the distribution operation. We distributed sources, distributed loads, and and so on, right? So distributed components. So this agent-based modeling would be ideal to model the today's dynamics in the power system. Okay. Okay. So so later you will see like we can easily model the individual agents, and then we can put the agents together to simulate the various scenarios, right? So it's just a matter of correctly modeling the individual agents okay, and model the interaction of the agents. And after that, you put hundreds agents, 1,000 agents, whatever, you can simulate the scenario based on the requirement. Okay. Okay. So if you compare the agent-based modeling versus the mathematical modeling, right? So the mathematical modeling relies on the equations, fixed parameters to predict the system behavior, right? So they often assume a linear relationship for easy solution, right? But you can do the nonlinear calculations as well, okay? So so while they provide very valuable insight and they can be also precise, okay, they lack the ability to capture the complexity and the variability. Okay, so they have the ability, but when you use that ability, the things will become more and more complex, and you need very high computational power to solve that kind of problem, right? But if you look at the agent-based model, right? Let's focus on the interaction of autonomous agents, okay, and allowing for emergent dynamics to arise from local rules. So as I said, you build the individual agent, and this dynamic will come from the behavior of that agents and the interaction of that agents with the others. That will kind of automatically come into the picture when the system starts running, right? Okay. I will show you so there are various tools that you can use for modeling the agent. So this is modeled by using the Python, and there is a library called the Mesa, right? And from that we can create the individual agent. So you can see, if you look at this code, you can see here I have a solar panel agent, right, with the necessary calculations and their interaction, right? And then I have weather agents, right? And the EV agents, right? So depending on your requirements, the agent, you can model it in detail or model it in the very less details, but depending on how accurate you want, right? And utility grid agent and so on, right? And you can see there's a step function in each of these agents, right? So each of these agent will run in a step. I will show a simulation. Okay. If I run this, so this is the interface. So you can see certain graphical interfaces there, which you can the model as you want, and then you can plot certain graphs, right? And you can choose different scenarios. So in this case, this electrical system, you have a tariff, right? So in this case, we have considered two kind of tariff, like the flat tariff and the time of use tariff, right? And the electric vehicles can have different charging structure. It can be uncontrolled, it can be vehicle to grid, grid to vehicle, and so on, right? And it can be slow charging, fast charging, or average charging, right? And then based on that, I can run this model. And if you run this model, you can see it's running in steps, right? So that's why that step function is there, right? So every step have each agent will take decision in every step, and each agent will interact with the other agents in every step, right? So this early in the morning, no solar, nothing, no EVs are going into the going here and there, right? And then when the time comes, you will see the EVs comes in, they start getting charged, right? And driving around, right? So you can see they are coming to the charging stations and getting charged, right? And once they get charged, they go back, right? So you can see as the time progress, how the things will behave. So you can do a very nice time simulation by using this agent-based modeling. So how much solar energy is available, depending on the cloud coverage, the weather, and so on, right? So that also you can model, right? So you can have a different agent as a weather agent to collect this weather information. So you can use there are online sites available with this weather information, right? Like weather.com and so on. So you can use their APIs to get the real-time weather information and feed into the system. So the system will, run as much as close to the real world scenario. So you can see the many different EVs are coming and charging, and how their state of charge of their batteries will vary, right? And so on. So you can see a very complex scenarios you can simulate by using a very simple set of agents, right? So that's the beauty of this agent-based modeling. Okay, right. So going back to my slides. So as I said, these agents, there's no like formal definition for this the agent, but these agents should have certain properties. They should be autonomous, right? So that means they can function independently in its environment, right? And interact with the other agents, right? And so you should build the agents in this manner. So they should be autonomous. They should not depend on your input or anything. So they should be able to take their own decision, right? And based on the interaction with the other agent, right? And the agent should be modular or self-contained, right? So it's an individual, right? With a set of characteristics, attributes, behavior, and the decision-making capability. So you model individual agent, right? So you don't think it as a whole system and model, right? You think of it as an individual agent. Now, if you are modeling a microgrid, right? So you have solar panels, you have electric vehicles, you have battery storage, you have loads, right? So they are interconnected, right? And exchange power in the microgrid, right? So the one option is you think of this as a whole model and build everything, their interactions and so on, and how the power flow and okay. But when it comes to the agent-based modeling, you don't worry about how they are interconnected at the beginning, right? And how the power flow, you don't worry about it, right? So you model individual. So you model the PV agent separately, EV agent separately, battery energy storage agent separately, and so on, right? And then, then you create the interaction with those agents, right? So there are various ways that you can do it by the message passing, or there are something called agent communication language. You can use that to build the interaction with the agent, right? And through these interactions and the agents, self attributes and characteristics, right? Agents use the agent's intelligence, the learn and the adaptability to adapt into the environment and learn from the environment, right? And as the simulation goes, the agent will adapt to the environment and behave as it will behave in a normal environment, right? Okay. So how you represent the intelligence, right? So there are various techniques that you can use, right? So you can use a rule-based system to represent the agent's intelligence, right? Or you can use the finite state machine, okay? Or you can use utility functions or the cost functions as we have seen in the mathematical model. Or you can use more advanced learning strategies like reinforcement learning or the game theoretic learning and so on, right? So, or you can go beyond that, going into ontologies and, facilitate the shared understanding among the agents, right? So it's depend on, how you want to build your agent. And so these are some the tools that will help you to build these agents. So I'm not going into detail on how to build agent and so on because of the time limitation, but you can investigate these tools. So most of them are actually free, right? So you can use the NetLogo. It has its own programming language, okay? And then the other one is the Repast. Right? So the Repast, there are two versions, one based on Java and one based on C. So depending on your expertise, you can choose, right? And there's another one called Mason. And what I have shown you is the Mesa, which is a library for Python. So you can integrate the other capabilities of Python to your agent-based modeling when you use the Mesa, right? Okay. And the intelligence you can incorporate it through the machine learning and AI approach, right? So you can use neural networks or you can use other type of the machine learning techniques. So you can use the Keras or TensorFlow or PyTorch to integrate the AI into the agent, right? Also, you can use these ontology tools like such as OWL and Pratik, right, to embed the ontologies into the agent. Okay, and okay, so you can use the reinforcement learning or the game theoretic model or any other advanced techniques to represent the agent behavior. Okay, so to give you a little interest, I will talk very little about the game theoretic agent. I don't have a slides or anything, but there's a nice, every game theoretic book will start from almost all from this example, which is called the prisoner's dilemma, right? So in here, what happens is a interrogator takes two prisoners, right? And they interrogate them, they put them into two different rooms and then interrogate them separately, right? So what happens here is now if the, let's say this is player one and player two, right? Now if, so these players have two options. One is confess, right, that he has done the crime. Okay. The other one is they can remain silent, right? So, okay. If the both remain silent, right, each will get a minor sentence for 1 year. They will only go to prison for 1 year if the both stays silent, right? But if both confess, they will get into a moderate sentences of 3 years if both confess, right? But the catch here is if one confess and the other remains silent, that means the one will confess that player one will say player two has done the crime and he give all the evidence to prove that player two has done the crime. Okay? And in that case, the one who confessed, that is player one, will go free and player two will go for 5 years for jail, right? Now imagine if you are a player one or if you are a player two, what you will do, right? So I will leave that part for you. So that is the essence of the game theory, right? So it's not your decision matters sometimes. It's the decision or it's the input or whatever interaction coming from the others will decide your fate, right? Or what you do in that particular scenario, right? I mean, you mean the agent or whatever, right? So probably you might have get the point, right? So it's all depend on the agents and their interaction. So it's not only depend on particular agent, but it all depend on the what other agents do in the environment as well. So which will help to capture the very dynamic and complex scenarios and how things will change in these scenarios very easily. Okay, but all you do is model the individual agents and their interaction. Okay, and then you will simulate many different scenarios. You know, by putting these agents into the environment. Okay. So this kind of simulation is very crucial for simulating the complex behavior of microgrids or smart grid, right? Which consist of many individual models, okay, and their interaction. Okay, so you can see this is the different agents. So you can see you have EV agent, solar agent, utility agent, weather agents, battery storage agent, main control agents, and you can see they have certain inputs and then the interactions between agents. So a very complex model, right? So it's a very basic model of the agent-based system that we have that I have simulated in a short while ago, right? That, yeah, I think I'm in that particular tab. Okay, yeah, that's the agent-based system that I have simulated earlier. Okay. So the advantage is that you can identify the by putting the agents into the simulation and observing their behavior, their outputs, and so on. You can identify the system level pattern, okay, or the system level behavior, that you can see that how the energy demand will vary, right? And energy demand from the grid and the battery storage will vary and so on. So depend on the behavior of the agent. So you can identify the system level pattern, okay, and you can uncover the hidden dynamics by using the agent-based modeling, right? You don't specifically model these dynamics, but when you put the agents into the simulation and based on the output they produce, you may able to uncover the certain hidden dynamics in the system. Okay. So there are a lot of applications in the agent-based modeling, right? So you can model the impact of certain policies, right? And how the market rule adaptation, how the market behavior, and how it can strengthen the operational resilience, right? And how it facilitates the interdisciplinary collaboration and the promoting the sustainable energy solution. By putting these agents and simulating the solutions, you can promote sustainable energy solution, not in only in the power sector, but in any areas. This is very popular in the the market behavior analysis and very popular among the economics, right? The people who do the economics, right? The agent-based modeling is very popular. Okay. 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 So as you have seen throughout this workshop, the future advancement will likely focus on the AI-driven approach, so which also include the AI-driven agent. And by using the agent-based modeling, with incorporating the AI-driven agents, you can do a real-time, model, real-time simulation of the different scenarios. So before you take the decision, you can simulate what will happen in the simulated environment with capturing many complex scenarios, and then based on that, you can take the decision. Okay. Right. So with that, I will conclude my presentation, and thank you very much.
A heartfelt thank you to our three distinguished speakers, Dr. Veerakun, Dr. Suravira, and Dr. Navaratna, for sharing their valuable expertise and insights with us today. Your presentations on applying machine learning in robotics, wireless communication, and power systems have provided us with a deeper understanding of intelligent engineering systems and their real-world implications. We sincerely appreciate your time and contribution to ICAIDS 2025. As a token of our gratitude and appreciation for sharing your valuable knowledge and time with us, I am honored to present this token of appreciation to Dr. WMMTS Veerakun on behalf of the ICARS 2025 Organizing Committee. Thank you very much, Dr. Veerakun, for your remarkable contribution to this tutorial session. Next, it is my great pleasure to present this token of appreciation to Dr. S.A.H.A. Suravira in recognition of your insightful contribution and the time you dedicated to today's tutorial. Thank you, Dr. Suravira, for your valuable presentation and for enlightening us with your expertise.